Parent functions are the topic of discussion today. We are going to learn 10 different kinds of parent functions. You see the list of them up there: linear, constant, identity, square and cubic, absolute value, square root, reciprocal, step, and the one you can't see, piecewise defined. Alright, we're going to look at each one of those, and we're going to discuss domain, range, x and y intercepts, any of these topics, increasing, decreasing, maximum, minimum for each one of these. Here's some generalizations about a linear function. Now, a in this case is my slope. I have my a set on 1. I have my b set on 1. So my y-intercept is at 1. It's whatever b is. We've discussed y-intercept in previous sections. A would be my slope of my linear function. If a is positive, it's increasing. So I'll write here that if the slope is positive, then it is increasing. If the slope is negative, then it's decreasing. Our domain, I look left and right to see what x can be. Negative infinity to positive infinity are all reals. I look at the range up and down. Negative infinity to positive infinity. And those are generalizations for a linear function. Here's our handy little constant function. He's very sweet. We have, I just graphed y equal 1. We have the domain. What can my x be? The domain can be anything from negative infinity to positive infinity. The range on this one looks like y is only one thing, and it's whatever your constant is, whether that be 1, 2, negative 3, 1.5. In this case, our y is 1 because that's the one that I graphed. And that's all the range is. Y is only 1 for this one. It's constant over the entire domain, so I would say that it's constant from negative infinity to positive infinity. And it is neither increasing nor decreasing. It is just constant. Has a y-intercept of whatever that y is. And that's my constant function. Here's our identity function, y equal x. Looks an awful lot like a linear equation. That's because it is. It's a linear equation with the slope being 1 and the y-intercept being 0. So it is a linear. It's just a specific case. But you're going to talk about the identity function quite a bit in this course, so we need for you to know the terminology. Of course, the domain and range are going to be the same as they are for a linear. The domain, negative infinity to positive infinity. The range, negative infinity to positive infinity. It's going to be increasing if we have a positive m or positive slope. And seeing as it is exactly y equal x and we'll have a positive slope, we won't be decreasing. What about constant? We won't have a constant area either. So here's our identity function. Here's our squared function. Our squared function is a quadratic. It's just the most general case, y equal x squared. For the domain, we look left and right. X can be anything. Remember, on domain, we had discussed that really unless you have a square root or unless you have a denominator, our domain, generally speaking, is going to be this negative infinity to positive infinity. Now the range, I look up and down. The range is going to be from 0 on up to infinity. There are no negative y's. It includes 0, so I make a square bracket on up to infinity. That's my range. Let's follow this line. We're looking at increasing and decreasing now. Let's follow this line. Looks like I'm decreasing from negative infinity all the way up to 0. And at 0, I start increasing. So from 0 on up to infinity, I'm increasing. My x and y intercept are exactly the same in this case. They're actually at 0, 0. And that's the general information for y equal x squared. And discussing symmetry here, this x squared is symmetric with respect to the y because it's the same on either side of this y-axis. We also call this an even function. So if it's symmetric with respect to the y, it's also an even function. All right, here's y equal x cubed. This is my cubic function. Once again, my domain, I don't have any restrictions on x, so my domain is going to be negative infinity to positive infinity. My range, that means what do my y's do? It's also going to be from negative infinity to positive infinity. If I follow this line from left to right, it looks like all I do is go up, so it is increasing from negative infinity to positive infinity. Now, if my leading coefficient, which we're going to discuss in the next section, if my leading coefficient is negative, it's actually going to flip this, and we'll have something different. We'll discuss how those transformations occur, actually. That's why we're going over all of these parent functions now. It is symmetric with respect to the origin. We call this an odd function. So it is symmetric with respect to the origin because if you took this little section here, made a wire out of it, and then kind of flip-flopped it, you would have exactly the same picture. Here's my absolute value function. My absolute value function, I don't have any restrictions on x. It can be anything, so my domain is once again negative infinity to positive infinity. The range, what do my y's vary from? That would be from 0 on up to infinity, including 0. So here's how I write that. I follow this line for increasing and decreasing. I follow this line to see where it's increasing, where it's decreasing. Looks like it is decreasing from negative infinity on up to 0, and it is increasing from 0 to infinity. As far as symmetry goes, it's the same on either side of the y-axis. So this would be y-axis symmetry, or we could also call this an even function. Either way, it's the same answer. Let's see, what about intercepts? Intercept right there at 0, 0. And I believe that's all for our absolute value function. Next, we have our square root function. Our square root function is this little guy right here. And note that if I were to keep drawing him, it would keep on going up. He would go up slower and slow, but he does keep on going up. What's his domain? Here's one of those things where I told you you have to watch out for whenever you have square roots. I can't have negatives in there. I can't have 0. So the domain is from 0 on up to infinity. That's what my x's can be. Let's look to see what the range is. Looks like it's starting at 0, and it's going to keep on going up and up and up. It's going to go up slow, but the range is still from 0 to infinity, even though it is going slow. Is increasing all along through this, so I'll say that it is increasing from 0 to infinity. Symmetry, there will be none, so I'll write none there because it's not the same in quadrant 1 and quadrant 2, nor is it a flip-flop into 1 and 3, so it definitely has no symmetry. Here's the reciprocal function. We're going to look at him quite a bit. We're going to do a lot of transformations with him over the next several weeks. The domain, what can my x's be? Oh yeah, we got a denominator here, and x can't be 0. Notice what happens here when x is 0. It goes shooting up to infinity and goes whoo, shooting down there to negative infinity. So we can't have 0 in our domain, but we can have everything else. So we can write it like this. And I was sure to use curvy brackets on my 0 to show that that point 0 was not included. Now the range. Looks like negative infinity is included. Don't think it ever crosses this x-axis. And looks like positive infinity is included. So I think the range looks exactly like the domain. Now, this is kind of a strange function when you look at increasing and decreasing. I'm move from left to right. Tell me what I'm doing. I'm going down. Yep, I'm going down. So it's decreasing from negative infinity all the way up to 0. Now let's start up here because I still have to move from left to right. What is this guy doing? He is still going down. So it's decreasing along this interval. Looks like the answer is the same all the way through here. Symmetry, it's the same in quadrants 1 and 3. It is a flip-flop, so we would say this has odd symmetry or origin. Either one of those two answers is correct. Intercepts, doesn't look like it ever crosses either the x or the y, so I'm just going to write none here. Alright, I'm going to draw the greatest integer function or step function here so you'll kind of understand exactly what it is. The best way I like to describe the greatest integer function is to describe it as, say, your birthday. When you are born, you are 0 years old. And you stay 0 years old until the day you turn 1. The day you turn 1, you are then 1. And you stay 1 until the day of your second birthday, at which point you then turn 2. Then you stay 2 until your third birthday, at which point you then turn 3, and you stay that way. And now you just continue the pattern up, and you would continue the pattern down. Of course, the analogy for your birthday doesn't really work when you're a negative age. That's supposed to be an open circle there, but didn't quite make it as open here. Try to make him a little more open. There he is. And here we are for the greatest integer function. And the pattern continues on down. All right. So now let's discuss our domain. What is our domain? Our domain on the greatest integer function is, well, x can be anything. So it's all real numbers, or from negative infinity to positive infinity. Now the range is a little different because I don't have fractions in here. In fact, the range might be 0, 1, 2, 3, -1, -2. So the range is the set of all integers. Integers are your positive, negative numbers, and 0. And this function is constant in between each integer. Constant totally in between integers. And that's all we have for our greatest integer function. Alright, here's our piecewise defined function. Now, I've gone ahead and graphed 2x plus 1 and -1/2 x minus 2. This is how I usually graph a piecewise defined. I just go ahead and graph the whole dumb thing. Then I see, here's my 2x plus 1 right here, the blue line. And it's only valid when x is less than or equal to 0. So it is actually not valid. Whoops. Let me get my right color here. It's actually not valid all in through here. So I'm going to erase the little guy. Alright. So he is valid now whenever x is less than 0. Then I have -1/2 x minus 2, and he's only valid for x greater than 0. So I'll get rid of him wherever he's less than 0. So I just go ahead and get rid of that little sucker there. Choo, 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 choo. And I just go ahead and graph the whole thing and then just erase the parts that I don't need. Now I do need to put a either open circle or closed dot. Looks like the 2x plus 1 has the closed dot, so that's this guy. I'll put a closed dot there. This guy has the open circle. And I have now graphed the piecewise defined. The domains and ranges for all of these are going to vary because you're going to always have two different things, two different equations that you're graphing. For this particular one, the domain is negative infinity to positive infinity. So I'll just write for this particular one, domain negative infinity to positive infinity. The range, let's look at this one. Looks like he comes up from negative infinity, he's all these numbers, and he only goes as high as 1. So the range on this one is from negative infinity all the way up to 1, including that point 1. Whoop, got a little carried away there. Anyway, there's our graphs of parent functions. Now we're going to use these parent functions to do graphical transformations in the next section.